Thank you. Yes, I am Sandor-Leahy from Northrop Grumman. I'm going to talk a bit about our project on developing a photonic spectrometer. I've been briefing this a few times at the tech forum, so this will be sort of a progress briefing on where we're at. Some key team members are listed there on the chart. We've got a pretty disparate team, everybody from photonic design experts to microelectronic fabrication integration to modeling and simulation. So it's a pretty wide-ranging team. Some of our key members are there. Couldn't unfortunately list everybody else, especially from our microelectronics foundry. We've done some fantastic work on developing the processes that you'll see in what we're building. So before I go on, the first time I briefed this at ESTF2020 called this science fiction. So I hope we're doing a good job of making it reality. So I'll show you some of the work coming up. Next chart, please. So just kind of a overview to motivate what we're doing. We've done hyperspectral imaging, hyperspectral sensors at Northrop Grumman for a very long time. So we've long had the concept of trying to use HSIs to basically be able to mimic multispectral sensors, and in particular to provide continuity with multispectral imagers. And of course, that's a key element of the sustainable land imaging requirements, is that they have continuity with such a long data record. And this is just an example of work done quite a while back with the Hyperion sensor that we built for NASA, and when it was behind Landsat 7 in the A-plane orbit, we were able to image both about a site with both Landsat and Hyperion, basically aggregate the Hyperion bands, and so that if you did careful aggregation, you could mimic the multispectral data from Landsat. So that kind of motivated our pursuit to get an HSI into sustainable land imaging in the long term. The next chart, please. And the other thing we've tried to work on for many years is to come up with an approach to make very small, compact sensors. And the idea that we've come up with is sort of a non-traditional idea, and it brings photonics and photonic devices into the picture here. So what our concept has been is to basically replace a lot of the free space optics that's typical of spectrometers, of course, and replace those with photonic integrated circuits. So the concept that you see here basically is a stack of photonic chips where those chips basically contain filters, waveguides, filters embedded in those waveguides, and then as light travels down these waveguides and through these filters, there's sequentially basically picked off at a detector that's embedded in the photonic circuit, and the light continues down the waveguide and is further detected. And basically, what you have here is a fully integrated package, so that the detectors are completely integrated with the waveguides and with the photonic circuit. So on the lower left of the chart there, this is Leahy integration, and the Leahy is an approach to integration of different technologies that we have in our microelectronics foundry. So it allows us basically to integrate, for example, in this case, gallium arsenide detectors with silicon dioxide waveguides. So we tried to bring this, attempting to bring this entire approach together to build a fully integrated device that is truly miniature, because the processes that we're using are microelectronic fabrication processes. So we're talking about extremely small devices. Next chart, please. So this program, we've heard from several folks here that this program was started a number of years back. It's in total, ours is in total a 5-year development program, funded by ESTO, of course. And our attempt is to, when we started this program, we had some internal research efforts going on, and we also had some other CRADs going on where we had actually shown the operation of a single filter, single waveguide, and an integrated detector using our Leahy process. And so now we are taking under this program, we're taking a pretty ambitious step forward to take those waveguides and basically build the entire sensor now. So in this effort, we're going to have where we have 128 cross-track pixels, basically, but each of those pixels now is a waveguide with the fully embedded filters, and it has embedded detectors and ROICs, and fully digital ROICs as well. So this effort is showing that we can basically build these spectrometers into bands that are pertinent to SLI, the bands that we see here in the SWIR. And as I say, also to develop the circuitry, the digital ROICs that go with it, and the integrated detectors. So we're trying to get this technology to TRL6 by the end of 2021. We started this project at TRL3. Next, please. So as I've mentioned, much of what's involved with this technology is, of course, developing microelectronic processes. What you see here are scanning electron micrographs of the waveguides themselves, an area that we call pockets, but basically those are where we are able to embed our detectors and integrate them with the photonic circuit. On the upper right one, basically what you're seeing is the waveguide, and then you're seeing what we call a pick-off waveguide, where the light comes down, is reflected back through that, and then into the detector that would sit in that pocket. So we've had to, under this program, develop a lot of, or I should say fine-tune a lot of the microelectronic fabrication processes that we have at our foundry, and fine-tune them to be able to perform in optical quality for this device. So what you see there is a prototype circuitry containing the waveguides and the metallization to carry the signals off of the detectors. Next, please. So on this chart we see in the upper right is one of our initial prototypes for a 1.3 micron 128 cross-track pixel 10 spectral filters at 3 nanometer spectral resolution spectrometer. So that's what you see in the upper right is the spectrometer itself. And basically, in our first iteration of these spectrometers, we integrated detectors, as I mentioned, gallium arsenide detector. And on the lower right photo, what you see there is the detector actually integrated into the pocket of the waveguide. So we basically sliced our devices in half to be able to show the quality of integration that we're able to get, and we're able to basically get our detectors, even our Dahi process, get them integrated within the 0.2 of a micron alignment accuracy, which is the kind of accuracy we need in order to feed those detectors from the output of the waveguide. So we've been able to do that consistently in multiple devices. It's been an excellent result for us. And then on top of it, along with the detectors, as I mentioned, we are integrating fully digital readout integrated circuits. So we've designed those circuits, but in the interim, for these initial prototypes, we've built what we're calling dummy or mechanical ROICs. So we integrate the detectors and the dummy ROICs just to prove out the functionality of these devices. Next, please. So this is kind of the newer data that I have since the last ESTF forum. Basically, we were able to demonstrate the operation of a spectrometer. This one is in the 1.29 micron wavelength range, and as mentioned, has 10 spectral channels at 3 nanometer resolution. And in this case, we integrated the detectors and these mechanical ROICs that I've described across the device, and then we did the optical testing to basically show that we were getting the results we wanted to see. And so in the upper right, that just shows the initial modeling that we undertook to model our device geometry. And the lower right is optical testing that we performed, basically looking at the throughput, the filter response, and the channel width, the resolution across our device. And we measured basically several spatial channels across the device, and spectral channels that were on different filters, and they were all consistent with one another. And so basically, we were able to get really nice consistency across across the entire spectrometer. And it was the first time we were able to show that this operated as a spectrometer, as a fully integrated spectrometer. So my last chart, and then I'll get off the get off the stage. So just a summary chart. As I say, we were quite happy to be able to demonstrate first ever demonstration of this functional photonic spectrometer. So that was quite encouraging, but right now we've moved on. What we're working on now is basically to try to optimize the performance of the design. We really want to optimize the throughput of the filter design. So we're in the midst of doing that now. We've completed the ROIC, and hopefully we'll have an opportunity to integrate those soon. And I just want to thank ESTO very much for the continued support we're receiving under this grant. Thank you.